So the Chesapeake Bay Foundation came out with this report, Manure's Impacts on Rivers, Streams, and the Chesapeake Bay. So I'll refer to several references, and there'll be several references at the end of this as well, that most of the information comes from. So when we talk about the Chesapeake Bay, I think we've noted this before, but we're talking about the largest bay estuary in the country, not the largest watershed, largest estuary. But it's still a large watershed, so we're talking about 64,000 square miles. So we've been dealing with watersheds that we define by acres, okay? Tens of acres, hundreds of acres. We're talking about multiple watersheds, but the process that we talk about in terms of watershed management and water use within those watersheds is the same regardless of scale. We just have more complex layers upon layers in this process. The biodiversity is very great within this watershed and within the bay. It's one of the ecological biodiversity areas recognized by the United Nations as being a highly biodiverse area within our watershed here, including the Chesapeake Bay. But the quality of the Chesapeake Bay water has been threatened for many, many years, as you all probably are aware of. Okay? So we have fisheries, and some of those fisheries have recovered, especially where the fisheries were just could be improved by tightly controlling the fishing process themselves. Where we've had greater issues with managing those fisheries is where that interfaces with the economic demands from the agricultural production within this watershed as well, because where we are now is that agricultural production leads to this excess nutrient buildup within the bay. That excess nutrient buildup decreases dissolved oxygen in the bay, and that dissolved oxygen, those dissolved oxygen levels threaten then the health of the biodiversity within the bay area. So you can see here that the nitrogen and phosphorus is one of the key areas here, and even though we can influence dissolved oxygen in other ways, and we have, so 20, 30, 40 years ago, this discussion would have centered around municipal wastewater and treating sewage and dealing with the sewage and the nitrogen and phosphorus and dissolved oxygen, BOD, going from sewage into the bay. That's largely been dealt with by engineers through engineered systems to improve that water quality, such that we don't really talk about that too much in this discussion. But we still have this depressed dissolved oxygen levels within the bay, which leads to decreased biodiversity, decreased production of oysters, crabs, and other economic resources within the bay waters as well. And that's a result mainly of the nitrogen and phosphorus production. And that nitrogen and phosphorus production now is coming largely from non-source pollutants. So as we have those non-source pollutants flow into the bay, we again get to model the bay by different areas in terms of the areas that are close to shore, the shallow water, which are going to be high productivity areas in terms of the amount of plant and animal life that lives in those areas. We have open water, deep water, and then deep channels. So we have multiple ecosystems even within the estuary that is the bay, and those are all going to be balanced with different water quality and water chemistry parameters within each of these segments within the bay itself. So we can keep that in mind as we talk about concentrations. We have to break these down into the components that we would model as engineers. So the point source pollutants are mainly going to be from those municipal and industrial sources, and because of National Point Discharge Elimination Standards, NPDES permits that were put in place about 20 or 30 years ago by the US EPA and the states as a agent for the US EPA laws and regulations, those point source pollutants are pretty well controlled and regulated. A lot of the nutrients and most of the nutrients coming into the bay today are from these non-point source pollutants. That's what happens to the fertilizer, including manure and industrial fertilizers that go onto the land areas and end up in our waterways and eventually into the bays. So this is from a few years ago, but you can see fertilizer, manure, and sludge application make up about 90% of the pie for phosphorus, okay, and about 75-ish% of the pie for nitrogen. The other percentage of the pie there is air deposition, right? But if we factor into the fact that a lot of the nitrogen that goes onto the land results on losses of ammonia, sources of nitrogen and phosphorus that volatilize from that manure and actually go into the air, almost all of this is going to be due to the application of the nitrogen and phosphorus onto land. So even though it's coming from the air, it starts on the land as a non-point source of pollutants. Yes, Skip.
How do they determine where those come from? Like, how do they
We're going to talk about that. We're going to go through, I'm going to show you step by step where they come from. I hope. Maybe not today, but by the end of next period, if not today. Good leading question. I'll tell you later. So in order to do that, Gail asked just the right question. How do we come up with those calculations? So we have to do the same thing that we've done throughout your engineering program where we look at the mass flow calculations. We look at the chemical parameters, the nature of the chemical applications of the nitrogen and phosphorus. We come up with a mass associated with that given amount of chemical put on the land. So how much of it do we have? How much of it is put on the land? Then we have to look at the utilization rate. How much is utilized in the production of the process that we're concerned with. So if we want to grow corn, how much of that nitrogen and phosphorus goes into the corn? If we want to grow chickens, how much of the corn goes into the chickens, and what do we get out of the other end that influences our nitrogen and phosphorus cycle? Okay? So we come up with a mass balance of utilization of those processes, and then we need to look at transport. It could be fluid transport, either as a gas or a liquid. Okay? But we need to take into account the direct transport of that fertilizer as well. So if we bring in industrial fertilizers into the bay, okay, so at Lowe's or Home Depot or wherever you go to buy your ChemLawn, wherever you go to buy your lawn fertilizer, if we bring those into the bay, okay, we're adding nitrogen and phosphorus into this watershed as well. If we take corn from the agricultural production and send it to the Midwest to raise cattle or somewhere else overseas, okay, we're exporting that nitrogen and phosphorus out of the watershed. So we need to take care and account for that transportation of the actual production of nitrogen and phosphorus as well as the production or transport by air and water within the bay as well. So then we come up with estimates of the mass flow rate into the watershed and out of the watershed the same way we would anything else, where we look at the concentration times the volumetric flow. Okay? Mass is equal to Q times C. So in this case, our runoff volumetric flow rate is going to be the runoff of the stormwater that we've just talked about modeling in this class for the last couple of weeks, times the concentration of the nitrogen and phosphorus that would be in that excess runoff as it goes into our waterways and eventually into the bay. So we use the exact same processes you use in basic engineering calculations, either in this class or in other of your sustainability classes, and we apply these same things to the model here. And in fact, we'll mention in the slides the Chesapeake Bay water model that utilizes these basic principles. So our main concern here with non-point pollution is going to be the stormwater runoff, and we'll have some of this materials in your notes so that you have it as a reference if you need it. I'm not going to go and read every slide. And this non-regulated stormwater runoff, okay, well, it's not regulated, meaning the water quality itself as it runs off a field doesn't need to meet a certain criteria. We're going to try and manage that, and the way we try and manage that is to come up with total maximum daily load regulations. So what's the maximum amount of nitrogen and phosphorus that can go into a waterway without negatively affecting that waterway? So rather than having a pipe and having something on the end of that pipe that treats or removes the nitrogen and phosphorus, we're not able to do that from a large field. That's not something that we have the technology to do right now before it gets into a waterway. So instead, we have to manage the upstream process of how we manage the application of that material on the land and optimize the application process so that most of the nitrogen and phosphorus more of it is utilized in the crops and gets contained within the crops, and less of it goes into the waterways as runoff and has a negative effect there.